Long before whales, before sharks as we know them, before the oceans felt stable and blue, there were periods when the sea itself turned against life, not gradually, not gently. There were moments in deep time when the chemistry of the ocean shifted so dramatically that entire food chains collapsed. Temperatures spiked by degrees that would devastate modern ecosystems. Oxygen drained from vast regions of water. Coral systems that had flourished for millions of years disappeared. In at least one event, more than 90% of marine species vanished. The ocean did not empty, but it changed, and the creatures that survived those chapters were not simply lucky, they were built differently. Some tolerated suffocating water, some hunted in dim, unstable ecosystems, some endured acidity that dissolved shells and skeletons. The fossil record shows extinction layers that look like planetary warnings. But between those layers, something else appears: adaptation. New predators emerging in ecosystems that had just collapsed, new body plans, new survival strategies. These were not peaceful seas, they were crucibles. So, what did it take to survive when the ocean lost its oxygen? What kind of predator evolves in water that turns toxic? How close did Earth's oceans come to becoming permanently hostile to complex life? And how many times did this nearly happen? Tonight, we descend into the deadliest oceans Earth has ever known, following the evidence written in stone and bone. But before we begin, I'd love to know where you're listening from tonight and what time is it there. It's always a joy to see how far these sleepy stories drift across the world. And if these gentle journeys bring you peace, a like or subscribe helps others find their way here too. Now, let your breath slow, let your body settle. So now take a deep breath, let your body relax, and let's go back to a time when survival in the sea was never guaranteed. The sea is moved not only by tides and storms, but by invisible balances held within its chemistry. Beneath the surface, life depends on exchanges too small to see: a steady rhythm of oxygen dissolved into moving water, carbon stored and released, heat carried across basins by slow circulating currents. When those balances hold, ecosystems spread in layered harmony. When they falter, the transformation can be vast and unforgiving. In certain ages, oxygen thinned across entire regions of the ocean. This condition, known as oceanic anoxia, does not arrive as a single dramatic wave. It unfolds as circulation weakens, as warm surface waters grow lighter, and resist sinking as the deep becomes isolated from renewal. Creatures that rely on dissolved oxygen begin to struggle. Gills pull at water that no longer carries enough breath. On the seafloor, burrowing animals vanish first, leaving sediments undisturbed. Above them, predators lose prey, and the structure of the community loosens from its base. Sometimes the chemistry shifts further still. In waters stripped of oxygen, certain microbes thrive and produce hydrogen sulfide, a gas toxic to most complex life. When this state spreads, the sea enters what scientists call oozemia, a condition where dark, sulfur-rich waters expand outward and upward. The boundary between survivable and lethal narrows, reefs falter, fish retreat or perish. The ocean begins to favor organisms that tolerate extremes once rare. At the same time, carbon dioxide dissolves more readily into warming seas. Its presence alters carbonate chemistry, reducing the availability of the building blocks that corals, mollusks, and countless plankton use to form shells and skeletons. In episodes of intensified acidification, delicate structures thin and fracture. Entire reef systems, built slowly over immense stretches of time, can crumble within comparatively brief intervals. Heat amplifies each of these stresses. Marine heat waves in deep time did not simply warm the surface, they reshaped currents expanded low oxygen zones, and accelerated chemical reactions throughout the water column. Stagnation followed as circulation slowed, particularly in enclosed basins and along supercontinents where coastlines diminished and exchange with the open ocean weakened. Nutrients accumulated unevenly, fueling blooms of microorganisms that consumed what oxygen remained. As plankton communities shifted or declined, the marine food chain unraveled from its smallest architects. Without a stable base, larger animals faced scarcity. Predators became fewer, then absent. What remained settled into layers of mud. In the rock record today, thin bands of black shale mark those intervals, sediments laid down in quiet, oxygen starved depths. Within their chemistry lie carbon isotope patterns and trace metals that speak of altered climates and disrupted cycles. Oceans respond swiftly to changes in temperature and atmospheric composition because they are deeply connected to both. Heat, gas exchange, and circulation bind sea and sky together. When the climate shifts, the ocean absorbs much of that change, and at times bears the burden in ways that reshape life across the planet. Across broad continental shelves, long before forests cast shadows on land, warm, shallow seas spread like luminous plains over the edges of stone. These waters moved gently across newly formed sediments, bathing coastlines that bore little resemblance to those of later ages. The air above carried oxygen that had only recently accumulated in meaningful amounts, and its presence in the sea was still uneven, rising and falling with subtle shifts in circulation and climate. During this interval, more than 540 million years in the past, oxygen was not yet a stable foundation for complex life. Concentrations fluctuated across regions and depths. In some basins, levels climbed high enough to support growing diversity. In others, they remained thin, limiting metabolism and size. The chemistry of the ocean felt provisional, as though the planet were testing what kinds of bodies it could sustain. Respiration became a powerful new possibility, unlocking greater energy for movement, sensation, and growth. With that energy came innovation. Life responded with extraordinary speed. Within a comparatively narrow span of geological time, simple forms gave way to organisms bearing hard shells, jointed limbs, compound eyes, and specialized mouths. This transformation, often called the Cambrian radiation, did not unfold in a tranquil setting. It occurred in ecosystems still learning how to balance abundance and scarcity. Shallow seas covered vast portions of the continents, creating expansive habitats where populations could expand, interact, and compete. Nutrients washed from exposed rock into coastal waters, fueling blooms of microscopic producers that formed the base of emerging food webs. With increased oxygen and growing ecological complexity, predation intensified. Among the early hunters were large arthropods, such as Anomalocaris, equipped with grasping appendages and sophisticated vision suited for scanning the water column. Their presence signaled a shift in evolutionary pressure. Bodies that once relied on softness and concealment began to acquire armor, spines, and burrowing behaviors. The seafloor, formerly a relatively undisturbed surface, became patterned with trails and tunnels as animals dug downward to avoid detection. Yet stability remained elusive. Because oxygen levels fluctuated and ocean chemistry continued to adjust, communities could expand rapidly and then contract just as quickly. Local die-offs left gaps that were soon filled by new forms, experimenting with alternative strategies. Some lineages thrived in well-oxygenated shallows, while others occupied marginal zones where conditions changed unpredictably. Ecosystems operated more like evolving laboratories than settled kingdoms. In this atmosphere of possibility and uncertainty, complexity deepened, sensory organs refined, Nervous systems coordinated movement with increasing precision. The interplay between predator and prey generated feedback that accelerated diversification. The seas of the Cambrian were neither uniformly gentle nor uniformly hostile. They were dynamic, responsive, and unfinished, a world in which oxygen's recent arrival reshaped biology from the cellular scale to the architecture of entire communities. In quiet slabs of stone lifted from the mountains of western Canada, a silhouette appears that once moved with deliberate grace through Cambrian water. Preserved within the Burgess Shale, its outline is both unfamiliar and precise, a body built not for drifting, but for pursuit. This was Anomalocaris, among the earliest large predators known from the fossil record, reaching lengths of about 1 meter in an age when most animals remained small and vulnerable. Its form did not resemble the armored trilobites that crept along the seafloor, nor the soft-bodied creatures that filtered particles from the water. Anomalocaris carried a flexible body lined with lateral flaps that rippled in coordinated waves, propelling it forward with controlled efficiency. At its head were two curved appendages, jointed and spined, designed for grasping and drawing prey inward. Between them sat a circular mouth composed of hardened plates arranged like a ring of teeth, capable of crushing or piercing depending on the target. Most striking were its eyes. Each was made of thousands of lenses, forming compound structures that granted acute vision across a broad field. In the filtered light of shallow Cambrian seas, such vision provided a decisive advantage. Movement could be detected from a distance. Subtle shifts in shadow signaled opportunity. With enhanced sight and active propulsion, Anomalocaris occupied a role that had been rare before, an apex hunter navigating open water rather than simply wading along the bottom. Its presence altered the evolutionary landscape. Prey species that had once relied on concealment faced a new pressure. Hard exoskeletons thickened. Some animals evolved the ability to enroll, tucking delicate limbs beneath protective plates. Others developed spines that made swallowing difficult or burrowed into sediment to escape notice. The relationship between predator and prey began to accelerate adaptation on both sides, an early arms race that shaped the architecture of marine life for millions of years to come. The Burgess Shale reveals these interactions in remarkable detail. Soft tissues that would normally decay were preserved in fine-grained mud deposited under specific conditions, capturing eyes, appendages, and gut contents. From these fossils emerges a vision of early oceans that were far from tranquil nurseries of simple forms. They were arenas of experimentation where mobility, perception, and defense intertwined. For organisms lacking shells or protective coverings, such waters demanded constant vigilance. Soft-bodied animals existed in a landscape where being seen often meant being consumed. Yet from that danger arose complexity. Neural coordination improved, body plans diversified, and ecological roles multiplied. Anomalocaris stands not as a monstrous anomaly, but as a sign that predation had become a powerful creative force, guiding evolution toward greater sophistication within the unfolding Cambrian seas. A hush fell over the water long before ice touched the continents. Currents that had once carried warmth across broad shelves began to cool, almost imperceptibly at first, then with gathering resolve. In the late Ordovician, the planet shifted into one of its earliest great ice ages, drawing down carbon dioxide and allowing vast ice sheets to expand across southern landmasses. As ice accumulated, sea level responded, retreating from coastlines that had long been submerged. Shallow seas, once teeming with trilobites, brachiopods, graptolites, and reef-building communities, grew narrower and fragmented. Sunlit platforms that had supported dense ecosystems were exposed to air or reduced to isolated basins. Habitat did not simply shrink, it unraveled. Populations that depended on stable, warm, shallow water found themselves confined to diminishing pockets. Migration routes vanished as shorelines shifted. Nutrient cycles adjusted to colder conditions, altering productivity in ways few organisms were prepared to meet. The cooling did not remain confined to surface waters. As climate patterns reorganized, ocean circulation shifted, redistributing heat and oxygen unevenly across depths. Some regions experienced enhanced mixing, while others became stratified. In many of the once thriving shelf environments, biodiversity declined rapidly. Fossil records from this interval reveal a stark contraction in species richness. It is estimated that roughly 85% of marine species disappeared during this extinction pulse, marking one of the first great biological crises in the oceans. Yet extinction was not uniform. While shallow communities suffered heavily, certain organisms endured in deeper or more stable refuges. Basins that maintained consistent temperature and circulation offered a measure of continuity. In these zones, some brachiopods, mollusks, and early chordates persisted. Their survival was less a matter of strength than of circumstance, occupying ecological niches buffered from the most severe environmental swings. When ice eventually receded and sea levels rose again, these survivors provided the foundation for renewed diversification. The Ordovician extinction illustrates how closely marine life is bound to sea level and climate. A drop in global temperature, amplified by shifting atmospheric chemistry and continental configuration, cascaded through habitats, dismantling systems that had flourished for millions of years. What had seemed expansive and secure proved contingent on narrow environmental thresholds. In the quiet layers of sediment deposited during this time, paleontologists trace the disappearance and reappearance of lineages across boundaries marked by subtle changes in rock and fossil assemblage. The record does not speak in dramatic ruptures, but in absences and returns, in the thinning of once common forms and the persistence of a few. From these remnants, marine ecosystems rebuilt, shaped by colder waters and new coastlines, carrying forward the memory of a world that had briefly narrowed under ice. Along tidal margins, where rivers met the sea, broad armored shapes moved through water the color of stirred sediment. In the Silurian world that followed the Ordovician crisis, coastlines were newly arranged and ecosystems were still in quiet repair. Life returned first to sheltered shallows and estuaries, where salinity shifted with each tide and resilience carried more value than specialization. Among the most formidable inhabitants of these transitional environments were the Eurypterids, often called sea scorpions. Some species reached lengths of nearly 2.5 meters, making them among the largest arthropods to have ever lived. Their bodies were segmented and shielded by tough exoskeletons, with broad swimming paddles extending from the rear limbs and powerful grasping appendages positioned near the head. They did not drift passively. They prowled. Eurypterids thrived in brackish lagoons, coastal embayments, and shallow marine shelves where conditions could fluctuate rapidly. Salinity could rise under intense evaporation or fall with seasonal influx from rivers. Such variability limited many organisms, but these predators endured it. Their compound eyes scanned murky water, and their forward limbs ended in robust claws capable of seizing trilobites, early fish, and soft-bodied invertebrates that ventured too close. The seas they inhabited were no longer the experimental realms of the Cambrian, nor the vast, stable platforms of earlier Ordovician warmth. They were recovering systems, marked by empty niches and reorganized food webs. Coral and stromatoporoid reefs began to re-establish structure in certain regions, offering habitat complexity that supported new communities. Jowed fish appeared in increasing diversity, introducing fresh competition and novel interactions. Within this shifting mosaic, Eurypterids occupied roles as agile hunters able to navigate both bottom and open water. Their exoskeletons suggest strength, yet they were bound by the constraints of molting, periodically shedding their armor to grow. During those vulnerable intervals, they relied on concealment and timing. Survival in recovering seas required not only size and force, but adaptability. Some species ventured briefly onto damp shorelines, leaving trackways in tidal flats that hint at short excursions beyond fully marine settings. Competition intensified as biodiversity climbed. Jawed vertebrates developed stronger bites and improved swimming efficiency. Smaller arthropods adopted defensive spines and swifter movements. The balance between predator and prey shifted again, this time within ecosystems shaped by the memory of extinction and the gradual return of complexity. Fossils of Eurypterids are found in sedimentary rocks that once formed quiet lagoons and shallow basins, their outlines pressed into layers that record fluctuating environments. They stand as reminders that recovery does not restore the past. It builds something altered, drawing from survivors and reshaping interactions. In the Silurian seas, giant arthropods ruled certain waters for millions of years, their presence woven into the evolving architecture of life as the oceans continued their long, dynamic transformation. Stone built by life once rose in luminous barricades beneath Devonian seas. For millions of years, reefs formed vast frameworks of coral and stromatoporoid sponge, stretching across tropical shelves and shaping coastlines far from land. These living structures filtered water, softened waves, and created intricate habitats where trilobites, mollusks, and armored fishes found refuge among branching calcite walls. Biodiversity flourished in their shadow, layered and interdependent, supported by warm temperatures and high sea levels that favored steady carbonate production. Yet this apparent stability concealed a fragile dependence on oxygen-rich circulation. As the late Devonian approached, environmental pressures accumulated. Continental arrangements shifted. Mountain building altered weathering patterns. Nutrients flowed differently into coastal basins. In many regions, deep waters began to lose oxygen. Circulation slowed across certain shelves, allowing stratification to intensify. Organic matter settling from surface productivity was no longer fully decomposed by aerobic processes. Instead, it accumulated in dark, quiet layers. The collapse was not a single abrupt moment, but a sequence of pulses spaced across geological time. Reef builders declined in waves. Coral frameworks that had expanded globally thinned, then vanished from some basins entirely. Without their scaffolding, the complex three-dimensional habitats they created dissolved into simpler seafloors. The change reverberated upward through the food web. Species that depended on reef niches lost shelter and feeding grounds. Specialized forms suffered most. Evidence of this transformation lies in black shale deposits that record intervals of widespread anoxia. These fine-grained sediments formed where oxygen scarcity prevented scavengers and burrowers from disturbing the seafloor. Within them are chemical signatures that speak of altered redox conditions and disrupted nutrient cycles. The rock bears witness to seas that had grown sluggish below the sunlit surface. Fish diversity, which had surged earlier in the Devonian, contracted sharply during these events. Placoderms, the armored-jawed fishes that once dominated coastal waters, diminished and ultimately disappeared. Lobe-finned and ray-finned lineages endured in reduced numbers, reshaping the trajectory of vertebrate evolution. The loss of reefs removed both nursery grounds and hunting arenas, narrowing ecological opportunities and favoring more generalized survival strategies. When reefs falter, the consequences extend beyond coral skeletons. They anchor entire systems of exchange between organisms, sediments, and seawater chemistry. In the late Devonian, as oxygen withdrew from depth and nutrient balances shifted, that anchor loosened. What had been vibrant carbonate platforms became quieter expanses punctuated by survival rather than abundance. The oceans did not empty, yet they were altered, their architecture simplified, their inhabitants fewer, carrying forward only those lineages able to endure in waters less forgiving than before. Weight moved through Devonian water with deliberate authority, a presence felt before it was seen. In seas where reef frameworks were thinning and food webs were under strain, one predator carried its defenses with it, plated and formidable. Dunkleosteus, an immense placoderm fish, reached lengths of nearly 10 meters, its body encased in thick, bony armor that shielded the head and thorax like a living fortress. Unlike later fishes with replaceable teeth, Dunkleosteus wielded sharpened bony plates that formed self-sharpening blades along its jaws. When these plates closed, they generated a bite force capable of crushing shell and bone alike, slicing through prey with startling efficiency. This mechanical power did not rely on speed alone, but on leverage and muscle anchored against rigid armor. In ecosystems destabilized by reef collapse and shifting oxygen levels, such versatility granted access to a wide range of prey, from armored invertebrates to other large fishes. The waters it patrolled were no longer the sprawling reef-dominated habitats of earlier Devonian warmth. Coral structures had diminished across many shelves, and oxygen loss in deeper layers altered distribution patterns of marine life. In this rearranged environment, apex predators required both resilience and adaptability. Dunkleosteus possessed both. Its armored plates offered protection against rivals, and perhaps against environmental hazards stirred by unstable conditions. While smaller, specialized species struggled as niches contracted, a heavily built generalist hunter could exploit whatever remained abundant. Armor, however, carried costs. The weight of bony plating required substantial energy for movement and growth. Success depended on ample prey and sufficient oxygen to sustain a large body. As late Devonian crises intensified, circulation patterns shifted further and ecological networks narrowed. Some basins experienced prolonged anoxia. Productivity fluctuated unpredictably. The very traits that had elevated Dunkleosteus to dominance may have rendered it vulnerable when resources declined and habitats fragmented. Fossil deposits from this interval capture its rise with clarity, yet its disappearance is abrupt. After flourishing through significant portions of the Devonian, Dunkleosteus vanishes near the close of the period, alongside many of its placoderm relatives. In subsequent strata, new fish lineages expand into roles once occupied by armored giants. Ray-finned and lobe-finned groups diversify, carrying forward vertebrate evolution in different forms. Within the stone, fragments of cranial armor and jaw plates remain as silent testimony to a predator adapted to turbulent seas. Dunkleosteus embodied both the power and the limits of armor in a failing ocean. It thrived amid instability for a time, its crushing bite echoing through reefs that were already fading, before yielding to the broader transformations reshaping marine life at the end of the Devonian world. Far below the reach of surface turbulence, the deep ocean relies on a quiet inheritance. Oxygen arrives there not through direct contact with the air, but carried downward by cold, dense water that sinks and slowly circulates across basins. This renewal can take centuries. When circulation weakens, the deep becomes isolated, cut off from its distant source of breath. What follows is not a storm, but a stilling. As climates warm or continental arrangements shift, surface waters may grow lighter and resist sinking. Stratification strengthens, layering the sea into distinct tiers that exchange less freely. Organic matter continues to fall from above, the steady rain of plankton remains and waste. In well-oxygenated settings, bacteria consume this material using aerobic respiration, drawing down oxygen but allowing balance to persist. When renewal falters, consumption outpaces supply. Oxygen levels decline, first gradually, then more decisively. In these dim depths, alternative metabolisms begin to dominate. Microbial communities adapt to the absence of oxygen by turning to other chemical pathways. Some reduce sulfate, producing hydrogen sulfide as a byproduct. The water takes on a different character, often enriched in dissolved iron and trace metals released from sediments under reducing conditions. The boundary between oxygen-rich and oxygen-poor layers sharpens, creating interfaces where distinct microbial blooms flourish. Green and purple sulfur bacteria, capable of photosynthesis under low light and high sulfide concentrations, may proliferate near these chemical boundaries. Their pigments, preserved in certain sedimentary rocks, serve as subtle testimony to episodes when toxic waters approached the surface. Within ancient black shales, geochemists identify molecular fossils and isotopic signatures that reveal prolonged euxinic conditions. These rocks form in basins, where bottom waters remain depleted of oxygen long enough to prevent disturbance by burrowing organisms. Life anchored to the seafloor responds first. Benthic invertebrates that rely on steady oxygenation retreat or perish, shell beds thin. Trace fossils marking burrows and feeding trails become scarce or vanish entirely from certain layers. Without bioturbation, sediments accumulate in fine laminations, each stratum undisturbed by the mixing activity that once animated the seabed. Higher in the water column, organisms that depend on benthic prey find their food base altered, leading to cascading adjustments. Anoxic episodes can persist for extended intervals or pulse in response to climate feedbacks. Their onset is often tied to increased nutrient delivery from continents, which stimulates surface productivity and enhances the downward flux of organic matter. The cycle tightens. More decay consumes more oxygen, reinforcing depletion at depth. Over time, entire regions of the ocean may operate under constrained chemical regimes unfamiliar to most complex life. In the stone record, these intervals are preserved not through spectacle but through absence, in the quiet, dark layers that speak of waters deprived of breath, reshaping ecosystems from the bottom upward. The air itself grew heavier with possibility during the Carboniferous, enriched with oxygen to levels far above those of many earlier ages. Vast forests spread across low-lying continents, locking carbon into thick peat that would one day become coal. With so much organic material buried and atmospheric oxygen rising, the boundary between land and sea became part of a tightly linked system each influencing the chemistry of the other in subtle but persistent ways. On land, arthropods attained remarkable size, supported in part by the diffusion of abundant oxygen through their tracheal systems. Dragonfly relatives spanned broad wings. Millipede-like forms stretched far longer than any that walk today. Though these giants inhabited swamp and forest, their existence reflected the same global chemistry that shaped nearby coastlines. The oceans received nutrients washed from dense vegetation and experienced fluctuations tied to glacial cycles unfolding across southern continents. Carboniferous seas were often shallow, extending over broad continental shelves in warm equatorial regions. These habitats supported crinoid meadows, brachiopod communities, rugose corals, and early sharks that patrolled the water column with increasing refinement. Productivity could be high, fueled by runoff and mixing in coastal basins. Yet the richness of these ecosystems did not equate to permanence. Sea levels rose and fell repeatedly as ice sheets expanded and retreated, alternately flooding lowlands and exposing them. With each oscillation, marine habitats expanded, fragmented, then reconnected. Shorelines shifted inland and outward over spans that, while vast in human terms, were geologically swift. Organisms adapted to particular depths or salinity ranges found themselves displaced. Some basins experienced restricted circulation when sea levels dropped, increasing the risk of localized oxygen stress. Others reopened during transgressions, allowing broader exchange and renewed diversity. Atmospheric oxygen, though abundant, did not guarantee uniform conditions below the surface. Temperature gradients, freshwater input, and basin geometry continued to influence how well deeper waters were ventilated. In certain settings, organic matter accumulated rapidly, and its decay consumed available oxygen, creating pockets of environmental strain beneath otherwise thriving shallows. The Carboniferous world held abundance and vulnerability in close proximity. Fish lineages diversified during this time, including early relatives of modern sharks and ray-finned forms that would dominate later oceans. Reefs persisted in modified configurations, though not with the same framework builders that had once characterized Devonian platforms. Life explored opportunities offered by high productivity, while repeatedly adjusting to the instability imposed by glacial rhythms. In sedimentary sequences from this period, alternating layers of marine limestone and terrestrial deposits record the pulse of advancing and retreating seas. The Carboniferous stands as a reminder that extremes, even those that foster growth, can coexist with delicate balances, shaping oceans that were fertile yet continually reshaped by forces far beyond the shoreline. Continents that had once stood apart began to draw together, closing ancient seaways and reshaping the margins of the world. Over millions of years, drifting landmasses fused into a vast supercontinent known as Pangea, stretching from pole to pole in an immense arc of connected terrain. As this assembly progressed, the character of the oceans changed with it, not in sudden upheaval, but through gradual restriction and reorganization. When coastlines shrink, so too do the shallow marine shelves that cradle much of ocean life. The joining of continents reduced the total length of shoreline, compressing expansive coastal habitats into fewer, broader margins. Interior regions of the supercontinent grew dry and continental, distant from moderating marine influence. Along the remaining coasts, broad embayments and epicontinental seas became more isolated, their exchange with the open ocean constrained by new geographic barriers. Ocean circulation adjusted to this altered geometry. With fewer connections between basins and a reorganized arrangement of currents, The global conveyor that carries heat and oxygen through deep waters began to slow in certain regions. Stratification intensified in restricted basins, particularly under warm climatic conditions. Surface waters heated beneath a powerful equatorial sun, while deeper layers received less frequent renewal. In places, oxygen levels thinned, creating pockets of environmental stress long before the final crisis would arrive. At the same time, tectonic forces beneath Pangea stirred deeper unrest. Volcanic activity increased across rift zones and along active margins as the supercontinent strained under internal pressures. Magmatic intrusions and eruptions released carbon dioxide and other gases into the atmosphere, subtly shifting climate over extended intervals. Though these emissions did not yet reach the scale of the later cataclysm, they contributed to warming trends that amplified stratification in the oceans. Marine ecosystems of the Permian were diverse, populated by brachiopods, ammonoids, reef-building organisms distinct from earlier corals, and a variety of fishes and invertebrates. Reefs reconstructed in modified forms along certain margins, while open marine communities spread across deeper basins. Yet beneath this diversity lay structural vulnerability. Reduced circulation limited the resilience of deep waters. Expansive continental interiors influenced weathering patterns and nutrient delivery, altering productivity in coastal seas. Sedimentary records from this time often show alternating layers that reflect shifting sea levels and changing redox conditions. In some basins, signs of intermittent anoxia appear, hinting at systems already nearing imbalance. The Permian Ocean before the collapse was not barren nor overtly hostile. It was dynamic and increasingly constrained. Geography, climate, and tectonics were aligning in a configuration that narrowed ecological flexibility, setting the stage for transformations that would soon test the limits of marine survival. In strata marking the boundary between Permian and Triassic worlds, a thin horizon appears that separates abundance from silence. Beneath it lie diverse assemblages of brachiopods, ammonoids, reef builders, and countless invertebrates shaped by millions of years of evolution. Above it, many of those lineages are absent. This interval, dating to roughly 252 million years ago, records the most severe marine extinction known in Earth's history. The trigger unfolded far from the sea, in a region that would one day be called Siberia. There, enormous volcanic eruptions known as the Siberian Traps released staggering volumes of lava across vast stretches of land. More consequential still were the gases expelled into the atmosphere, particularly carbon dioxide and methane liberated from heated sediments. These emissions intensified the greenhouse effect, driving rapid global warming over geologically brief spans. As atmospheric temperatures climbed, surface oceans absorbed heat and additional carbon dioxide. Warming reduced the solubility of oxygen in seawater, while added carbon dioxide altered carbonate chemistry, lowering pH and placing stress on organisms that depended on calcium carbonate to build shells and skeletons. Reefs that had endured earlier crises faltered again. Circulation patterns weakened in a progressively warmer, more stratified ocean. Deep waters, already prone to stagnation in certain basins, expanded their oxygen-poor domains. In some regions, anoxia transitioned into widespread eusinoia. Microbial sulfate reduction intensified, producing hydrogen sulfide that accumulated in bottom waters and may have episodically reached higher levels. Such conditions would have been lethal to most complex marine animals. The ocean, once a buffer against atmospheric instability, amplified the crisis through its own chemical feedbacks. The toll was immense. Estimates suggest that between 90 and 96% of marine species disappeared during this event. Entire ecological guilds were erased. Trilobites, which had persisted through multiple earlier disruptions, vanished completely. Many coral and sponge lineages failed to recover. Fish diversity contracted sharply, with only a fraction of groups surviving to seed Triassic ecosystems. Geochemical evidence underpins this narrative. Carbon isotope excursions in sedimentary rocks reveal massive perturbations to the global carbon cycle, consistent with rapid input of isotopically light carbon from volcanic and sedimentary sources. Sulfur isotopes document shifts in ocean redox states, while trace metal concentrations indicate prolonged oxygen deficiency in many basins. Black shales deposited during this interval bear the mark of widespread anoxia. The Great Dying did not erase life entirely, yet it reduced marine complexity to a shadow of its former breadth. Ecosystems that emerged afterward were simpler, dominated by opportunistic species capable of tolerating extreme warmth, acidity, and low oxygen. In this boundary layer of stone, the ocean's capacity for transformation is etched with stark clarity, marking a moment when planetary systems aligned to challenge the persistence of nearly all marine life. In the aftermath, etched into stone at the close of the Permian, the ocean did not fall silent, yet its voice changed to something thinner, more tentative. Where layered reefs and diverse communities had once constructed intricate marine cities, wide stretches of seabed lay simplified. Survival did not belong to the largest or most elaborate forms, but to those able to persist in diminished worlds. Among the land vertebrates that endured the terrestrial collapse were dicynodonts, such as Lystrosaurus, sturdy herbivores that would come to dominate early Triassic landscapes. Their marine relatives were not direct swimmers, yet their resilience reflects a broader pattern shared across realms. In coastal and marginal marine environments, only a narrow selection of lineages crossed the boundary from Permian abundance into Triassic renewal. Brachiopods, once extraordinarily diverse, were reduced to a few surviving groups, their shells thinner and their ecological range constrained. These survivors occupied habitats where conditions, though harsh, remained within tolerable limits of temperature and oxygen. Reefs, as architectural structures built by complex communities, largely vanished. In their absence, microbial mats spread across the seafloor in places where grazing animals had declined. These mats, layered sheets of bacteria and algae, formed low, undulating carpets that trapped sediment and stabilized substrates. For a time, they replaced the three-dimensional frameworks once created by corals and sponges. Their dominance signaled a return to simpler ecological organization, reminiscent of much earlier eras when microbes structured shallow marine landscapes. The pattern of survival favored small body size and flexible physiology. Organisms with rapid reproductive cycles and broad environmental tolerance possessed an advantage in fluctuating conditions. Species that required narrow temperature ranges or highly oxygenated waters struggled to persist. In contrast, those capable of enduring warmth, temporary hypoxia, and variable chemistry were more likely to carry their lineages forward. Ammonoids, though nearly extinguished, rebounded quickly from a handful of ancestral forms, demonstrating how even a slender branch can seed renewed diversification. Sedimentary records from early Triassic seas reveal communities low in diversity but high in ecological dominance by a few opportunistic groups. Bivalves expanded into roles once held by more specialized organisms. Certain foraminifera continued to calcify even under stressed carbonate chemistry, hinting at physiological mechanisms that buffered against acidity. The survivors were not superior in the conventional sense. They were simply aligned with the altered parameters of a transformed ocean. From these reduced assemblages, recovery unfolded gradually. Complexity would return, but not immediately. For a span measured in millions of years, marine ecosystems remained comparatively sparse, shaped by the limits imposed by lingering warmth and restricted circulation. The creatures that endured the Great Dying embodied adaptability, carrying forward genetic threads through a planetary bottleneck, ensuring that the sea, though changed, would never be wholly empty. Time did not hurry the sea back into fullness. In the early Triassic, coastlines bordered waters that were quieter than in ages past. Their communities thinned, but not extinguished. Recovery began as a gradual layering of life upon life, a slow return of diversity guided by survivors that had endured the harshest interval in marine history. Evolution proceeded with patience, exploring openings left vacant by vanished lineages. Biodiversity rebounded unevenly. Some regions remained stressed for extended spans, marked by low species counts and simple food webs. Elsewhere, pockets of stability allowed gradual expansion. Ammonoids diversified from a narrow ancestral base, radiating into varied forms that occupied different depths and feeding strategies. Bivalves increased in abundance, their flexible lifestyles enabling them to inhabit shifting substrates and fluctuating chemistry. The structure of marine ecosystems began to grow more intricate, though it would require millions of years to approach earlier levels of complexity. Predation intensified once more, but with new participants. Early representatives of groups that would later dominate entered the oceans. Marine reptiles, descended from terrestrial ancestors, adapted to life in water with streamlined bodies and modified limbs. Among them were the ichthyosaurs, whose fish-like silhouettes and powerful tails allowed efficient swimming through open seas. Their emergence introduced fresh dynamics into marine food webs, adding large, fast-moving vertebrates to ecosystems that had recently been reduced to opportunistic survivors. Other reptiles followed, including placodonts with crushing teeth, suited for feeding on hard-shelled prey in shallow environments. These animals occupied ecological niches vacated during the extinction, reshaping predator-prey relationships. Fish lineages continued to diversify as well, filling mid-level roles and supporting expanding trophic hierarchies. The seas were not yet crowded, but they were increasingly active. Reef ecosystems, once devastated, began to reassemble in altered configurations. Instead of relying solely on earlier framework builders, new communities formed around scleractinian corals, which would become central architects of later reefs. These structures developed cautiously, growing where temperature, chemistry, and circulation permitted stability. For a time, microbial structures coexisted alongside coral frameworks, reflecting a transitional state between simplicity and renewed complexity. Geochemical indicators suggest that environmental stress lingered into portions of the Triassic, including episodes of warming and localized oxygen depletion, yet the overall trend leaned toward diversification. As climates gradually moderated and circulation improved in some basins, the ocean supported increasingly elaborate interactions. Food webs deepened, niches multiplied. The Triassic recovery oceans did not restore the Permian world. Instead, they forged a new configuration of life, drawing from resilient ancestors and newly evolved forms. Within these waters, the foundations of later Mesozoic marine dominance were laid, not through sudden abundance, but through steady, adaptive expansion across a reshaped planet. Out in the widening expanse beyond coastal shelves, a new silhouette began to claim the open water. It did not crawl from reefs nor stalk from tidal shallows, but cut through offshore currents with fluid precision. Ichthyosaurs, marine reptiles descended from terrestrial ancestors, reshaped themselves for life far from land, their bodies streamlined into forms strikingly similar to later dolphins, though separated by vast stretches of time. Their skulls tapered into elongated rostra lined with conical teeth suited for grasping swift prey. Vertebrae stacked into flexible spines that powered crescent-shaped tails, generating sustained propulsion across broad pelagic zones. Limbs transformed into stiffened flippers, stabilizing movement through layered currents where maneuverability determined survival. In these recovering Triassic seas, where ecosystems were still assembling their hierarchies, such efficiency granted dominance. Among their most remarkable features were their eyes. Some species possessed enormous ocular openings, ringed by bony plates that supported large spherical lenses. These adaptations allowed keen vision in dim conditions, extending their hunting range into deeper waters where light attenuated rapidly. There, shoals of fish and cephalopods provided sustenance in a food web expanding outward from its post-extinction base. Enhanced sight offered advantage in pursuit, detection, and navigation across vertical gradients of the water column. Ichthyosaurs were not bound to shore for reproduction. Fossil evidence reveals embryos preserved within adult bodies, indicating live birth in open water. This reproductive strategy freed them from the need to return to land, unlike many earlier reptilian forms. By giving birth at sea, they fully embraced a pelagic existence, sustaining populations across vast oceanic territories without dependence on coastal nurseries. As apex predators, ichthyosaurs exerted pressure on mid-level consumers that had recently diversified. Their presence structured trophic layers in evolving ecosystems, reinforcing complex interactions among fish, invertebrates, and other marine reptiles. Competition arose with emerging plesiosaurs and larger predatory fishes, yet ichthyosaurs maintained prominence for millions of years, radiating into varied body sizes and feeding specializations. Their success reflects more than anatomical innovation. It signals a transition in the character of marine life following catastrophe. Open ocean habitats, once sparsely populated during the immediate aftermath of extinction, became arenas for renewed evolutionary experimentation. In these waters, mobility and sensory acuity shaped survival as profoundly as tolerance had in earlier stressed environments. Through sedimentary sequences spanning the Triassic and into later periods, ichthyosaur skeletons appear in abundance, preserved in offshore deposits that once lay beneath deepening seas. Their streamlined forms capture a chapter in which reptiles mastered the pelagic realm, transforming recovering oceans into corridors of motion and predation, carrying forward the expanding narrative of life's resilience within Earth's ever-changing seas. A subtle shift in the sky can echo through the sea in ways that leave no immediate scar upon the surface. When volcanic provinces pulse or carbon stored in sediments returns to the air, carbon dioxide accumulates above the waves. The ocean, vast and responsive, absorbs a portion of this gas. As it dissolves into seawater, it reacts with water molecules, forming carbonic acid and releasing hydrogen ions that gently alter the balance of marine chemistry. Within seawater, calcium and carbonate ions drift in quiet partnership, available for organisms that build shells and skeletons from calcium carbonate. Corals, mollusks, brachiopods, and countless microscopic plankton draw upon this reservoir, extracting material to form protective structures and support their bodies. When additional carbon dioxide enters the system, hydrogen ions bind with carbonate, reducing its availability. The shift does not shatter reefs in a single instant, yet it narrows the margin within which calcifying life can thrive. Geological records reveal intervals when this balance tipped decisively. Layers of sediment preserve signs of weakened shells, reduced reef growth, and abrupt changes in species composition. In some strata, the abundance of heavily calcified organisms declines, replaced by forms less dependent on robust carbonate frameworks. Microscopic fossils of foraminifera show thinning walls and altered morphologies, subtle testimonies to stress within seawater chemistry. During episodes of rapid carbon release in deep time, such as those associated with large-scale volcanism or methane destabilization, acidification often coincided with warming and oxygen stress. The combined pressures amplified ecological disruption. Carbonate platforms that had flourished for extended spans experienced pauses in growth or transitions to alternative builders. In certain intervals, carbonate dissolution surfaces appear within reef sequences, indicating periods when seawater chemistry favored erosion over accumulation. Though separated from those ancient events by immense spans of time, the underlying chemistry remains unchanged. Modern oceans absorb anthropogenic carbon dioxide in much the same manner, forming carbonic acid and shifting carbonate equilibria. Measurements today document declining pH and reduced saturation states of aragonite and calcite in surface waters, echoing processes inferred from the rock record. The pace and context differ, yet the chemical pathways are consistent with those traced through past crises. Ocean acidification does not act alone. It interweaves with temperature, circulation, and nutrient dynamics. Its influence unfolds quietly, often detectable first in the smallest architects of marine ecosystems. Across deep time, the story preserved in limestone and shale demonstrates that when carbon moves rapidly into the ocean atmosphere system, seawater responds with a change in character, reshaping the conditions under which shells form, reefs rise, and marine communities endure. Water covered vast continental margins during the Jurassic, spreading into broad interior basins and linking distant coasts beneath a climate that was persistently warm. Polar regions lacked permanent ice, and sea levels stood high, submerging low-lying land beneath shallow epicontinental seas. In this greenhouse world, currents circulated through expansive tropical belts, distributing heat across a planet whose shorelines were softer and more sinuous than before. Within these waters, marine reptiles reached imposing scale and specialization. Plesiosaurs drifted and surged with elongated necks that extended from compact bodies, their four broad flippers moving in coordinated strokes that resembled underwater flight. Some species fed on small fish and cephalopods, probing shoals with agile movements of head and neck. Others, more robust, carried heavier skulls suited for seizing larger prey. Alongside them swam pliosaurs, shorter-necked but immensely powerful, with massive heads and jaws lined with formidable teeth. These animals occupied roles at the summit of marine food webs, exerting influence across multiple trophic layers. The ecosystems that sustained them were increasingly intricate. Reef communities rebuilt around scleractinian corals, forming complex habitats that sheltered invertebrates, fish, and juvenile reptiles. Ammonites spiraled through the water column in extraordinary diversity, serving both as predators and prey. Bony fish groups expanded in variety, and early relatives of modern sharks refined their sensory capabilities, navigating by electric cues and scent within turbid coastal waters. Each lineage interacted within a web of exchange that extended from plankton near the surface to hunters in deeper realms. Warm global temperatures enhanced productivity in many regions, though local variations in circulation created zones of differing oxygenation and nutrient supply. High sea levels promoted widespread shallow habitats, allowing reefs and carbonate platforms to flourish across continental shelves. These expansive marine settings supported dense communities and fostered competition among large predators. Plesiosaurs and pliosaurs coexisted through niche differentiation, varying in size, diet, and preferred hunting grounds. Sedimentary sequences from the Jurassic preserve abundant skeletal remains, often articulated in fine-grained deposits laid down beneath tranquil waters. Their distribution across multiple continents reflects the interconnected nature of Jurassic seas, unimpeded by polar ice barriers. Such connectivity facilitated broad dispersal and evolutionary experimentation, enabling marine reptiles to radiate into numerous forms over millions of years. The Jurassic oceans were neither static nor immune to episodic disturbance, yet for extended intervals they sustained some of the most formidable marine vertebrates ever to inhabit open water. In their warmth and breadth, these seas supported a tapestry of life woven from coral frameworks, cephalopod swarms, fish shoals, and reptilian giants, each contributing to a complex and enduring marine world. Not all crises arrive with fire or impact. Some unfold through quiet layering as boundaries form within the sea and grow sharper with time. In certain intervals of Earth's history, the oceans separated into distinct tiers, warm and buoyant waters resting above cooler, denser layers with little exchange between them. This stratification limited the downward transport of oxygen, creating conditions in which depth became increasingly deprived. When climates warmed and rainfall patterns intensified, rivers carried enhanced loads of nutrients from continents into coastal waters. Phosphorus and nitrogen entered marine basins in greater quantities, stimulating surface productivity. Plankton bloomed across sunlit layers, drawing carbon from the atmosphere and forming the foundation for dense biological growth. Yet what flourished above carried consequences below. As these organisms died and sank, microbial communities decomposed the descending organic matter, consuming oxygen in the process. If circulation remained sluggish, replenishment from the surface could not match the pace of consumption. Oxygen minimum zones expanded, first within restricted basins, then across broader regions of continental margins. Water that once supported active benthic ecosystems became inhospitable. Species adapted to moderate depths retreated or vanished, leaving sediments less disturbed and food webs simplified from below. The expansion of low oxygen regions did not eliminate life entirely. Rather, it reorganized it. Certain bacteria and archaea thrived within oxygen-depleted waters, altering nitrogen and sulfur cycles in ways that further reshaped chemistry. Small invertebrates, capable of tolerating hypoxic stress, persisted where more demanding species failed. Fish populations shifted vertically or geographically, seeking pockets of higher oxygen content. Some predators found their hunting ranges compressed into thinner layers near the surface or along well-ventilated currents. For large marine reptiles and fishes, reliance on sustained oxygen supply constrained distribution. Apex predators required abundant prey and sufficient dissolved oxygen to support high metabolic demand. As oxygen minimum zones widened, these hunters faced reduced habitat and altered migration patterns. The compression of viable depth ranges intensified competition in remaining oxygen-rich waters, subtly reshaping trophic interactions. Sedimentary records from such intervals often preserve laminated deposits and geochemical markers indicative of reduced ventilation. Elevated concentrations of certain trace metals accumulate under low oxygen conditions, while shifts in nitrogen isotopes signal altered nutrient cycling. These signatures reveal that oxygen minimum zones were not fleeting anomalies but recurring features tied to climate, nutrient input, and circulation. The sea, though immense, is sensitive to imbalance. When warmth, runoff, and stratification converge, depth can lose its breath without spectacle. In those intervals, marine ecosystems adjust to narrower bands of habitability, carrying forward only those lineages capable of enduring diminished oxygen in a world still rich at the surface, yet increasingly constrained below. There are chapters in the Cretaceous, written not in bones, but in darkness. Across multiple continents, geologists have traced broad bands of black shale laid down in basins that once lay beneath warm epicontinental seas. These deposits do not represent local stagnation alone. They mark intervals when vast stretches of the global ocean slipped into oxygen deprivation, a series of events now known as oceanic anoxic episodes. During the Cretaceous, greenhouse conditions prevailed. Polar ice was absent, sea levels were elevated, and shallow inland seas spread across low-lying regions. Within this warm framework, pulses of intensified volcanism released substantial quantities of carbon dioxide into the atmosphere. Large igneous provinces, forming over extended intervals, injected greenhouse gases that amplified global temperatures and altered ocean circulation patterns. As surface waters warmed, stratification strengthened, limiting vertical mixing between oxygen-rich upper layers and deeper basins. At the same time, elevated carbon dioxide enhanced chemical weathering on land. Rivers delivered increased loads of nutrients, particularly phosphorus and nitrogen, into coastal environments. Surface waters responded with massive plankton blooms, their growth visible in the geochemical record as heightened organic carbon burial. What thrived in sunlight above created consequences below. When vast quantities of plankton sank and decomposed, microbial respiration consumed dissolved oxygen at depth more rapidly than it could be replenished. The expansion of oxygen-poor waters during these intervals was extensive enough to leave a global signal. Black shale deposits formed where bottom waters remained persistently depleted, preventing disturbance by burrowing organisms. These sediments often contain high concentrations of organic carbon and trace metals associated with reducing conditions. Carbon isotope excursions recorded in marine carbonates and organic matter reveal large-scale disturbances to the global carbon cycle, tied to both volcanic input and enhanced burial. Food chains grew unstable as oxygen minimum zones broadened and habitats contracted. Benthic communities declined in affected basins, and certain groups of ammonites and foraminifera experienced turnover events. Reef systems persisted in some regions, but faced stress where chemistry shifted and circulation faltered. Pelagic predators encountered altered distributions of prey as nutrient pulses reshaped productivity patterns, sometimes intensifying surface abundance while diminishing deeper refuges. Yet, the Cretaceous oceanic anoxic events did not extinguish marine life on the scale of the Permian catastrophe. Instead, they punctuated an otherwise flourishing era with episodes of constraint and reorganization. In their wake, ecosystems adjusted, some lineages diminishing, others diversifying in newly configured niches. The black shales remain as quiet evidence that even during intervals of warmth and apparent abundance, the ocean's interior can change profoundly when carbon, climate, and circulation converge in delicate imbalance. Along the margins of the late Cretaceous seas, long bodies moved with sinuous power, neither fish nor reptile of the old kind, but something newly perfected for open water dominance. Mosasaurs, descended from terrestrial lizard ancestors, had fully committed to marine life, their limbs transformed into broad paddles and their tails extended into strong, crescent-shaped propulsors. Some species reached lengths approaching 15 meters, rivaling the largest marine reptiles of earlier eras. Their skulls reveal a design built for versatility and force. Unlike rigid jaw systems, mosasaurs possessed loosely articulated bones that allowed their mouths to widen and adjust as they fed. A secondary set of pterygoid teeth along the roof of the mouth helped grip struggling prey, drawing it inward once seized. This flexibility enabled them to consume a broad range of animals, from fish and ammonites to smaller marine reptiles. Fossilized gut contents confirm these varied diets, preserving scales, shell fragments, and bone within the rib cages of individuals entombed in marine sediments. By the late Cretaceous, marine ecosystems had grown increasingly complex, layered with diverse plankton, schooling fish, cephalopods, and multiple tiers of predators. Mosasaurs occupied the apex in many of these settings, patrolling epicontinental seas that spread across portions of what are now separate continents. Warm climates and high sea levels fostered expansive, shallow habitats, sustaining rich food webs that could support such immense hunters. Their dominance did not arise in isolation. Sharks diversified alongside them, refining sensory systems and feeding strategies. Large, bony fish occupied mid-level roles, while ammonites continued their intricate evolutionary dance through spiraled shells and drifting currents. Mosasaurs integrated into this tapestry as powerful generalists, capable swimmers with keen vision and acute smell, tracking prey across broad distances. Sedimentary deposits from inland seas preserve their remains in abundance, particularly in formations that once lay beneath calm, sediment-laden waters. Articulated skeletons and isolated vertebrae alike testify to their widespread distribution. For millions of years leading to the close of the Cretaceous, they represented the pinnacle of reptilian adaptation to marine life, combining terrestrial ancestry with pelagic mastery. Yet, their reign coincided with planetary conditions that would soon shift irrevocably. As part of the broader, late Cretaceous marine community, mosasaurs thrived within ecosystems that appeared stable and productive. Their flexible jaws and formidable size symbolized evolutionary success within those warm seas. When the final disruption arrived at the end of the period, they stood among the dominant predators of their time, emblematic of an ocean that had once again built complexity after earlier catastrophes. Unaware that another turning lay ahead, a single distant flash altered the chemistry of the sky and the rhythm of the sea. At the close of the Cretaceous, an asteroid struck what is now the Yucatan Peninsula, forming the structure known as Chicxulub. The impact released energy beyond comprehension, vaporizing rock, igniting wildfires, and sending shock waves through atmosphere and ocean alike. In coastal regions near the strike, water surged inland in immense waves, scouring shorelines and depositing chaotic layers of sediment that remain visible in outcrops around the Gulf of Mexico. These tsunamis radiated outward across connected seas, disturbing marine basins thousands of kilometers away. Sedimentary records preserve rip-up clasts and mixed deposits that testify to sudden, violent agitation. Yet the most far-reaching consequences unfolded not in the first hours, but in the months that followed. Dust, soot, and aerosols injected high into the atmosphere dimmed sunlight on a global scale. Photosynthesis faltered as light struggled to penetrate the stratospheric veil. In surface waters, phytoplankton communities that formed the foundation of marine food webs experienced rapid collapse. These microscopic producers fix carbon and generate much of the ocean's organic matter. When their productivity plunged, the flow of energy to zooplankton, small fish, and higher predators contracted abruptly. Sediment cores across the world record a sharp decline in planktonic foraminifera at this boundary, their once abundant shells replaced by impoverished assemblages dominated by a few opportunistic forms. Without steady primary production, marine food chains unraveled from the base upward, suspension feeders lost nourishment, predatory fish and marine reptiles that depended on dense prey populations faced scarcity. Even in regions distant from the crater, ecosystems faltered under the combined stress of darkness, cooling, and chemical changes in seawater resulting from acid rain and altered carbon cycling. The extinction was swift in geological terms. Ammonites, long successful inhabitants of Mesozoic oceans, vanished entirely. Mosasaurs and other large marine reptiles disappeared alongside many planktonic groups. In contrast to some earlier crises tied primarily to warming or anoxia, this collapse began with an impact that interrupted sunlight itself, halting the engine of marine productivity. Recovery would come, but only after the atmosphere cleared and light returned to surface waters. For a brief yet decisive span, the ocean entered a state of profound contraction. Its complex networks reduced to remnants capable of enduring diminished energy flow. In boundary layers enriched with iridium and shocked minerals, the story of this marine collapse is written clearly, marking a moment when an event from space reshaped life beneath the waves with sudden and lasting force. Beneath the turmoil that reshapes surface waters, there are realms where change arrives more slowly. The deep ocean exists beyond the reach of storms, beyond the direct glare of sunlight, beyond many of the rapid fluctuations that unsettle coastal and pelagic ecosystems. In the wake of catastrophe, whether driven by warming, impact, or chemical upheaval, these depths can at times function as refuges, not untouched, but buffered by their physical stability. Temperature at depth remains remarkably constant compared with the surface. Once water masses sink and settle into abyssal basins, they retain their character for extended intervals, insulated from seasonal shifts and short-term climate oscillations. Even during global warming events, the deepest layers respond with a muted and delayed signal. This steadiness can offer a narrow window of survival for organisms adapted to cold, low-light environments where variability is already minimal. Energy in the deep sea does not depend on photosynthesis alone. Organic matter descends as a slow, continuous snowfall from above, providing sustenance for benthic communities even when surface productivity declines. After the asteroid-driven collapse that dimmed sunlight, this rain of detritus diminished sharply, yet not instantly. Carcasses of plankton, fish, and larger animals sank through the water column, temporarily enriching abyssal plains. Scavengers, equipped to capitalize on sporadic abundance, fed on these pulses. Flexible diets and slow metabolisms favored persistence in a world of irregular supply. Benthic fossils from boundary layers reveal that some deep-dwelling foraminifera and invertebrates crossed extinction thresholds that erased many surface counterparts. While species turnover was significant, complete annihilation was rare in certain abyssal assemblages. Trace fossils continue through intervals of crisis, indicating that burrowing life persisted, though often at reduced diversity. The sedimentary record suggests contraction rather than total collapse. Depth alone does not guarantee protection. Severe anoxia, acidification, or warming can penetrate into deep basins under particular configurations of circulation. Yet in events primarily initiated at the surface, abyssal ecosystems sometimes experience dampened extremes. Their inhabitants are already adapted to low energy conditions, reduced oxygen concentrations, and stable cold temperatures. Such traits can confer resilience when rapid perturbations sweep across shallower habitats. Recovery often radiates outward from surviving pockets. As surface conditions stabilize and productivity resumes, energy once again filters down. Lineages that endured in the depths contribute genetic continuity, repopulating broader regions over extended spans. The deep sea, vast and remote, serves not as a sanctuary immune to change, but as a slow reservoir where life can persist through intervals that overwhelm more dynamic zones, maintaining threads of continuity beneath upheaval above. Far from continental shelves and drifting carcasses, in darkness that has never known dawn, the seafloor opens in quiet fissures. Through these fractures, heated water rises from within the crust, enriched with dissolved minerals drawn from deep rock. Around these hydrothermal vents, the ocean hosts ecosystems that do not depend on sunlight, but on chemistry carried upward from the planet's interior. When superheated fluids meet cold seawater, minerals precipitate and build chimney-like structures along the vent fields. The surrounding water becomes rich in compounds such as hydrogen sulfide, methane, and dissolved metals. In most settings, such chemistry would prove hostile to complex life. Here, it serves as fuel. Microorganisms harness energy, not through photosynthesis, but through chemosynthesis, oxidizing chemical compounds to generate organic matter. In doing so, they form the base of entirely self-sustaining communities. Microbial mats coat vent surfaces, layering bacteria and archaea across mineral deposits. These primary producers support larger organisms that have evolved intimate relationships with them. Tube worms, some reaching impressive lengths, lack digestive systems in the traditional sense. Instead, symbiotic bacteria living within their tissues perform chemosynthesis, supplying nutrients directly to their hosts. Clams and mussels cluster near vent openings, similarly housing internal microbial partners that convert chemical energy into biological growth. Such ecosystems have likely existed for much of Earth's history, appearing wherever tectonic activity creates pathways between crust and ocean. During intervals when surface productivity collapses, whether through darkness, acidification, or warming, vent communities may remain comparatively insulated. Their energy source does not rely on light or on the stability of atmospheric conditions. As long as geologic heat continues to drive circulation through seafloor cracks, chemical energy remains available. This independence does not render vent systems invulnerable. Changes in ocean chemistry, temperature, or circulation can still alter their structure. Yet evidence from certain extinction intervals suggests that deep chemosynthetic communities experienced less severe turnover than many surface-dependent ecosystems. Fossil traces of vent-associated organisms appear across multiple geological boundaries, indicating continuity through events that devastated reefs and pelagic food webs. Hydrothermal vent ecosystems reveal that life can anchor itself to planetary processes beneath the surface. In ancient seas, as in modern ones, they represent pockets of persistence fueled by Earth's internal heat rather than by the sun above. Within their mineral towers and microbial tapestries lies a reminder that even when surface oceans falter, the deep may sustain living networks sustained by chemistry, offering resilience rooted in the restless geology of the seafloor. Beneath continental margins, within sediments held under pressure and cold, methane rests in crystalline cages of ice, known as hydrates. These deposits remain stable so long as temperature and pressure conditions persist, locking vast quantities of carbon within the seabed, yet they are sensitive to change. When oceans warm or pressure decreases, the crystalline lattice can destabilize, releasing methane gas into surrounding water and, eventually, the atmosphere. One of the clearest ancient examples of such disruption occurred during the Paleocene Eocene thermal maximum, a geologically brief interval marked by a pronounced rise in global temperature. Carbon isotopes preserved in marine and terrestrial sediments reveal a rapid injection of isotopically light carbon into the atmosphere ocean system. Although volcanic activity and other sources contributed, destabilized methane hydrates along continental shelves likely amplified the event, releasing additional greenhouse gases that intensified warming. The temperature increase unfolded swiftly in geological terms. Surface waters warmed by several degrees within a span measured in thousands of years, a pace far quicker than many previous climatic transitions. As heat accumulated, ocean stratification strengthened and circulation patterns adjusted. Increased carbon dioxide dissolved into seawater, lowering pH and altering carbonate chemistry across marine basins. Deep sea ecosystems, normally buffered by stable conditions, experienced unusual stress. Benthic foraminifera, microscopic organisms that inhabit seafloor sediments and build calcareous shells, suffered significant extinction during this interval. In sediment cores from multiple ocean basins, their once diverse assemblages contract abruptly at the onset of warming, replaced by fewer, more tolerant species. The combination of elevated temperature, reduced oxygen, and acidified conditions likely exceeded the tolerance thresholds of many deep-dwelling forms. Sedimentary layers from the Paleocene-Eocene boundary display distinct clay-rich horizons and shifts in carbonate content, reflecting dissolution in deeper waters. Geochemical signatures indicate perturbations in both carbon and oxygen cycles, consistent with rapid greenhouse amplification. The methane release and associated warming did not eliminate marine life broadly, yet they triggered a profound reorganization of ecosystems, particularly in deep environments long considered stable. The recovery that followed unfolded over tens of thousands of years as carbon was gradually drawn down through weathering and organic burial. Ventilation patterns readjusted and temperatures moderated. The Paleocene-Eocene thermal maximum stands as a reminder that carbon stored beneath the ocean floor can, under certain circumstances, re-enter circulation and amplify climatic change. In the rock record, this episode is preserved as a sharp and coherent signal, a moment when methane release contributed to climate chaos and reshaped life from surface waters to the ocean depths. In the cold stillness of abyssal plains, where light has never traced a silhouette, size can take on unexpected proportions. Across various intervals of Earth's history, deep marine environments have fostered forms of arthropod life that seem enlarged beyond their shallow water relatives. Among them were ancient isopods and other crustaceans whose bodies echoed familiar shapes, yet expanded under the peculiar conditions of depth. The deep sea imposes constraints, unlike those of sunlit shelves. Pressure increases steadily with descent, compressing gases and demanding structural resilience from any organism that inhabits these realms. Arthropods that ventured into such zones carried rigid exoskeletons well suited to resisting deformation. Their segmented bodies distributed force evenly, while jointed appendages allowed movement across soft sediment where currents were faint. Gigantism in deep dwelling crustaceans likely arose from a confluence of factors: cold temperatures, slow metabolic processes, extending growth periods, and reducing the energetic cost of maintaining larger bodies. Food arrives sporadically, descending from above in intermittent pulses of organic material. A larger size can aid in energy storage and in traveling greater distances to locate nourishment across sparse terrain. Oxygen levels in certain deep basins have, at times, remained low but stable, favoring organisms adapted to efficient respiration under constrained supply. Slow metabolism becomes an asset in such settings. Many deep sea arthropods exhibit reduced activity, conserving energy between feeding opportunities. Their movements are deliberate rather than swift, their life cycles prolonged. In ancient oceans marked by episodes of anoxia in shallower regions, these traits may have conferred resilience. While surface communities fluctuated sharply, some deep environments maintained comparatively steady, if austere, conditions. Fossil evidence of ancient deep water arthropods is less abundant than that of coastal species, yet their presence is inferred from both body fossils in fine-grained sediments and from trace structures etched into seafloor deposits. Certain lineages display morphological continuity across extinction boundaries, suggesting that deep habitats provided partial refuge during times of environmental upheaval. Early crustaceans diversified into niches ranging from scavengers to detritivores, occupying roles that depended on recycling organic matter rather than on direct reliance upon photosynthetic productivity. Modern giant isopods, found in contemporary abyssal zones, offer a living analog to these ancient strategies. Their broad, armored forms and slow, patient movements mirror patterns that have likely persisted for millions of years. In the deep sea, where scarcity and stability intertwine, arthropods evolved bodies attuned to pressure, cold, and intermittent abundance. Through such adaptations, they carried their lineages quietly across ages of change, enduring in darkness while the surface world shifted above. Along tropical margins, where clear water once shimmered above intricate carbonate structures, there were intervals when the architecture of life quietly dissolved. Reefs are not merely clusters of coral skeletons. They are living frameworks that bind thousands of species into layered communities, offering refuge, feeding grounds, and spawning sites across compact spaces. Within their crevices, fish shelter from predators. Within their shadows, invertebrates filter and graze. Along their surfaces, symbiotic relationships weave together algae and coral into mutual survival. Across multiple eras, these hubs of diversity have risen and fallen in response to shifting chemistry, temperature, and circulation. Their collapses follow patterns that echo through deep time. In the late Devonian, reef frameworks declined as oxygen loss and nutrient imbalance reshaped shallow seas. During the end Permian crisis, complex reef builders nearly disappeared, replaced for a time by microbial communities. In later warming intervals, acidification and stratification weakened carbonate production, leaving shelves barren where vibrant ecosystems had stood. When reefs vanish, the effect cascades through the food web. Specialized herbivores lose grazing grounds, small fish lose shelter. Predators that depend on dense reef communities must adapt or relocate. The disappearance of structure compresses ecological space, narrowing niches and intensifying competition in remaining habitats. Even organisms not directly dependent on reef substrate feel the consequence, as planktonic larvae lose settlement sites and coastal productivity shifts. Predatory species often suffer indirectly. Without reef fish populations sustained by intricate habitats, larger hunters face reduced prey availability. In some intervals, generalist predators expand into alternative zones, while specialists decline sharply. The removal of reef complexity alters nutrient cycling, sediment stability, and local hydrodynamics, amplifying environmental stress already in motion. Stone preserves these absences with striking clarity. Fossil reef complexes, once towering carbonate edifices, sometimes appear capped abruptly by layers lacking the usual framework builders. Limestone transitions into fine-grained sediments where burrows and coral fragments cease. Entire reef tracts become graveyards of broken skeletons, their growth halted within relatively narrow geological spans. In certain formations, scattered coral heads lie embedded in sediments that signal unfavorable chemistry or temperature, silent evidence of interrupted construction. Yet reefs have also demonstrated an ability to return. New builders emerge from surviving lineages, reconstructing frameworks in altered forms after extinction intervals pass. The specific architects may differ across eras, yet the ecological function reassembles, binding biodiversity once more into compact, resilient systems. The vanishing of reefs marks more than the loss of beauty. It signals a broader disruption within marine balance. In deep time, their absence has served as both consequence and indicator of stress, revealing how intimately the health of shallow carbonate worlds is tied to the larger chemical and climatic rhythms of the sea. Evolution does not move toward comfort, it moves toward possibility within constraint. In oceans that have warmed, cooled, stratified, acidified, and darkened across deep time, survival has often favored those organisms willing to bend their biology toward the edge of tolerable conditions. From these pressures emerged a gallery of extreme adaptations, each shaped by the specific challenges of unstable seas. Armor arose again and again where predation intensified or chemistry turned hostile. Thickened shells, reinforced exoskeletons, and bony plates did more than deflect bites. They buffered internal chemistry from fluctuating pH and offered protection in environments where injury could prove fatal in oxygen-poor water. In placoderms, eurypterids, trilobites, and countless invertebrates, hardened structures became both shield and anchor, enabling life to persist amid heightened competition and environmental stress. Gigantism appeared in multiple lineages, from marine reptiles to deep-sea arthropods and enormous fish. Larger bodies can stabilize temperature, deter predators, and travel greater distances in search of food across vast pelagic zones. In nutrient-rich intervals, gigantism allowed apex predators to dominate. In colder depths, it provided efficient energy storage and slower heat loss. Yet size demanded abundant oxygen and prey, rendering giants vulnerable when ecosystems contracted. In dim and deep waters, eyesight evolved beyond surface norms. Enlarged ocular structures, sensitive retinas, and reflective layers enhanced the ability to detect faint light or bioluminescent signals. Ichthyosaurs developed immense eyes to pursue prey in low illumination. Certain deep-dwelling fish evolved tubular vision, adapted to upward scanning silhouettes. Such specialization allowed hunting in vertical niches where light scarcely penetrated, expanding the habitable column of the sea. Not all adaptations favored speed or strength. Slow growth strategies and extended lifespans became viable in environments marked by limited energy. Some bivalves and deep sea organisms grow incrementally over decades, conserving resources and reproducing steadily rather than explosively. Reduced metabolic rates enable endurance during prolonged scarcity, a quiet strategy contrasted with rapid boom and collapse cycles in shallower systems. Opportunistic feeding has likewise proven enduring. Generalist diets permit survival when preferred prey disappear. Scavengers, capable of consuming carrion, detritus, or varied invertebrates, can persist through abrupt ecological shifts. After extinction intervals, such adaptable feeders often dominate early recovery phases, filling niches before more specialized forms reemerge. Together, these adaptations reveal a pattern. Extreme seas do not reward a single solution, but a range of biological experiments attuned to specific pressures. Armor, size, heightened vision, patience, and dietary flexibility each represent pathways carved through constraint. In the vast record of marine history, life has responded to deadly oceans not by retreating from complexity, but by refining it into forms capable of enduring instability and reshaping ecosystems in the wake of upheaval. Not all success in the ocean is measured by dominance or size. Some lineages persist not through dramatic transformation, but through continuity, carrying ancient body plans forward across upheavals that erased more specialized forms. Their endurance suggests a different strategy, one grounded in balance rather than excess. Horseshoe crabs trace their ancestry deep into Paleozoic seas, their outlines remarkably consistent across hundreds of millions of years. Broad, domed carapaces shield soft underparts, while multiple jointed legs maneuver them across sandy bottoms. Their physiology tolerates wide ranges of salinity and temperature, allowing habitation in both coastal shallows and slightly deeper waters. Reproduction linked to tidal cycles places their eggs in nutrient-rich zones, supporting larvae adapted to transient conditions. Despite environmental shifts that extinguished countless marine arthropods, horseshoe crab lineages persisted with comparatively modest alteration. Nautiloids embody a similar continuity. Their coiled shells, divided into chambers connected by a siphuncle, regulate buoyancy with understated precision. In contrast to their ammonoid relatives, which diversified rapidly and vanished entirely at the close of the Cretaceous, nautiloids maintained slower rates of speciation and a narrower ecological range. Their conservative life history strategies, including slower growth and extended maturation, may have shielded them from the volatility that favors rapid turnover yet invites abrupt extinction. Simplicity does not imply primitiveness. These organisms possess refined physiological mechanisms shaped by deep time. Horseshoe crabs carry blue blood rich in copper-based hemocyanin, enabling efficient oxygen transport under variable conditions. Nautiloids rely on well-integrated buoyancy control that permits vertical movement through changing pressure regimes. Their anatomical designs avoid excessive specialization, preserving flexibility across habitats. Genetic resilience likely contributes to such longevity. Populations distributed across broad geographic ranges maintain variability that buffers against regional disturbances. Reproductive strategies that produce numerous offspring increase the probability that some will survive unpredictable shifts. Moreover, occupying ecological niches that do not depend on narrow environmental thresholds reduces vulnerability when oceans warm, cool, acidify, or stratify. Throughout marine history, lineages that diversify rapidly often dominate temporarily, then decline when conditions change. In contrast, Organisms built for endurance persist in the background, less conspicuous, yet consistently present. Fossil records reveal their silhouettes, recurring across stratigraphic boundaries that mark extinction events. They appear above and below layers that signify abrupt loss, bridging intervals of crisis with minimal interruption. Such stability through simplicity offers a quiet lesson within the broader narrative of deadly seas. Endurance does not always arise from innovation at the edge, but from designs balanced within tolerable limits. In horseshoe crabs and nautiloids, the ocean retains living connections to distant epochs, reminders that resilience can reside in forms refined not for spectacle, but for survival across immeasurable spans of time. Across the span of oceans we have traveled, patterns begin to echo forward. The record held within stone is not distant from the present. It continues to resonate in currents moving through today's seas. Ancient intervals of warming, oxygen loss, and chemical disruption offer a long perspective against which modern change can be measured. Surface temperatures are rising once more, and the ocean absorbs most of the excess heat retained by the atmosphere. Warmer water holds less dissolved oxygen, and stratification intensifies as lighter surface layers resist mixing with cooler depths below. In several regions, oxygen minimum zones are expanding, compressing habitats available to fish and invertebrates that require higher concentrations. These dead zones resemble, in smaller scale, the low oxygen events preserved in black shales from earlier eras. Carbon dioxide entering the ocean lowers pH and alters carbonate chemistry, complicating shell and skeleton formation for corals, mollusks, and planktonic calcifiers. Coral bleaching, driven by elevated temperature, disrupts the partnership between coral animals and their symbiotic algae. When prolonged, bleaching can lead to mortality and reef degradation. Past reef collapses followed similar disturbances, where warming and acidification outpaced the tolerance of carbonate builders. The comparison is not exact. Today's oceans differ in continental configuration, circulation patterns, and the evolutionary makeup of life, yet the markers of stress align in recognizable ways. Rapid carbon input, warming measured over short intervals in geological terms, stratification, oxygen decline, and ecosystem reorganization appear together in several ancient transitions. In those chapters, biodiversity contracted and communities shifted toward more tolerant forms. Deep sea benthic organisms, surface plankton, reef dwellers, and mobile predators each respond differently to environmental change, but none exist in isolation. Food webs link surface productivity to abyssal plains. Chemical balance ties atmospheric composition to ocean health. Ancient records demonstrate that, when thresholds are crossed, adjustments can be profound and lasting. History matters because it stretches beyond human memory, revealing consequences invisible within a single lifetime. The fossil and geochemical archives show that oceans are dynamic systems capable of resilience, yet also of abrupt transformation. Recovery has occurred before, though often overspans far longer than human timescales. Lineages endured, others vanished, and ecosystems reorganized under new constraints. To view modern change against this backdrop is to recognize continuity rather than inevitability. Past deadly seas illustrate both vulnerability and adaptability. They reveal that carbon cycling, oxygen distribution, and biodiversity remain tightly interwoven. In the quiet testimony of rock layers and fossil assemblages, ancient oceans extend a measured perspective, reminding us that the present moment is part of a far older narrative shaped by chemistry, climate, and the persistent response of life. Water covers most of the planet, and yet it is never still in its long history. Continents drift, currents reroute, chemistry shifts, and temperatures rise or fall with forces both gradual and abrupt. The ocean that seems familiar from a shoreline is only one expression in a continuum that stretches across immense spans of time. There have been chapters when circulation slowed and oxygen thinned, when carbon surged into the atmosphere and dissolved into surface waters, when reefs fractured and deep basins recorded loss in dark sediments. There have also been intervals of renewal, when new lineages expanded into emptied niches and complexity reassembled from remnants. Collapse and recovery are not opposites. They are phases within the same planetary rhythm. Life has approached thresholds of disappearance more than once. Entire groups that dominated for millions of years ended within comparatively narrow slices of geological time. Yet extinction has never erased all possibility. In every crisis, certain organisms endured, sometimes through strength, sometimes through flexibility, sometimes through traits that seemed modest until conditions changed. Adaptability, whether expressed as tolerance of temperature, breadth of diet, or resilience of physiology, has often determined continuity. The sea itself is powerful but not fixed. Its chemistry responds to volcanic outpourings, to weathering of mountain ranges, to the arrangement of continents that steer currents and regulate heat distribution. Its ecosystems respond in turn, shifting composition as environmental boundaries move. Stability is a temporary balance maintained within broader motion. Creatures from ancient deadly seas illustrate this dynamism. Armored fish, towering marine reptiles, deep-dwelling scavengers, and quiet survivors such as horseshoe crabs and nautiloids all occupy different points along a spectrum of response. Some flourished only briefly under particular conditions, others threaded their existence across multiple upheavals. Together they form a tapestry of persistence and transformation, preserved in rock and sediment as testimony to resilience under constraint. What appears constant within a single lifetime is, in geological perspective, part of an unfolding sequence. Shorelines migrate, habitats expand and contract, and the interplay between atmosphere and ocean continues to evolve. The present ocean, rich and vulnerable, participates in that same ongoing story. There is calm in recognizing motion without imagining permanence. The record of past seas offers context rather than alarm, perspective rather than prediction. Earth has changed, often dramatically, yet life has responded with innovation and endurance. The ocean always changes, and within that change, continuity persists, carried forward by organisms shaped by a planet that has never stood still.